Hey guys, it's Mr. Koser here. Thank you for your feedback from today on the blog. I really appreciate it. I want to take a little time and chat with you a little bit about what we're up to and what we're going to keep going on in this lab with the ramps, and then we'll move on to the next thing. Hey, I spent the day today up in the Twin Cities at an avid data mining workshop. Mrs. Lyon and I were there with some teachers from East and teachers from around the country looking at how to work with data in our avid program. It was pretty neat. You guys worked with your video today on uniformly accelerated particle motion and the one and only Mr. Barry. Thank you for your work, and thank you again for your blog post. It's neat to see what you're doing. I appreciate that. I see some of you successfully posted information to our blog. Thanks for doing that. That's very helpful so I can get a quick look at what you're doing. I see these graphs from third hour, and I see a set of graphs here from first hour. Thanks for doing that. What I want to do is point out a couple things about these videos that we might want to work on. One of the things I notice is some of your videos are showing graphs that are parabolic and going uphill like this, and some of your graphs are showing downhill videos like this, downhill graphs. Both of those work because they're curved and they show accelerated motion, but really to make the analysis easier, I want to have you change your graph so you have an uphill plot like this. What that means is just a matter of moving the origin around. You notice this is Charlie and Justin's movie from first hour, and when I move the origin around, you can see how it changes the data on the graph, but it doesn't change the shape of it. I've rotated the origin so the positive x-axis is pointing down the hill, and I'm going to show you what it looks like if I choose a different x-axis. If I choose the negative x-axis down the hill, then I get a graph that curves down and to the right, kind of like some of the ones you folks have. What I'd like to have you do is make sure that the positive x-axis, the one with a yellow dot, is the one that is the direction that the motion is going. And the reason I want you to do that is so that we all have uphill parabolic curves, which is going to make the analysis a little more simple. So once you get that and you have an uphill curve, I think it'll help. You'll notice when you plot the velocity graphs, like the ones I have down here below, they're pretty straight lines. Obviously some bumps in here, but they're pretty straight lines. Also, to keep track of which is which, a handy thing to do is to use the legend. You'll notice in these two videos I have legends in the top right corner. To access that, if you double click on the video, you can turn on and off this option over here called legend, and that's handy because it'll let you know which one is which. Yesterday I walked through how to make that t-squared column. I won't take the time to do that right now, but if you need directions on how to create a t-squared column down here, just check the previous video and I'll show you how to do that. I'm going to go ahead and switch to that at this point. Okay, so once you've made the t-squared column, you can switch the position graph over to t-squared, and you'll notice these get fairly straight. The reason that's good news is because that shows us that it is a parabolic relationship. That is, when we graph distance versus the time squared, we get a pretty linear relationship. In a few minutes we'll come back and we'll want to put a straight line on this. But let's focus our attention down here on the velocities for just a minute. As I suggested yesterday, on these velocity graphs we want to put slopes on both of them. So we're going to ask for a linear fit right here and choose slopes on both of them. And the point is that, hey, we have two different ramps with two different slopes. These are awfully alike. These two graphs aren't terribly different. One's at 1.86 meters per second, and the other's at 1.943 meters per second, but they're fairly close. The goal is for you to recognize different slopes there, and as I've seen several of your sheets, we're looking for this kind of thing, a greater change in speed versus time and a lesser change in speed versus time. For both of those, what you want to do is write a slope intercept equation, a y equals mx plus b, and really one big goal is to figure out what that slope means. I hope that'll be significant to you and you can work towards that. Now you notice I did ask you to find the position time squared graph down here, and the point is that that graph gets pretty linear. This red one I'm going to use for an example, and we're going to take this red one and we're going to look at the linear part of it that's a little bit later in the graph. I'm going to choose to fit just the linear part of it, and you notice you get a nice straight line, and again I'm fitting against t squared here. And you get a nice straight line, and I want you to point out the slope of that straight line is 0.6853. That's what I want you to go back and look at on this sheet when we create that line, or when we draw that line again. And the slope you can use to write the equation. Still a linear line, still a y equals mx plus b, but you'll have a slope for this line, and you'll have a slope for the line up above, and the goal is to be able to look at those two together. The reason I have this question down here is I want you to compare the slope that you find on the position time graph with the slope that you find on the velocity time graphs. There's a connection there. I want to see if you can come across what that is. The generalized equation is a chance for you to express, hey, how does the distance relate to the slope of this graph, which I think you'll be able to connect. You may need to go a little digging, do a little digging to find an equation, but I want you to try to connect those two things. And as you've already done, many of you, go ahead please and make the motion map to show the two different motions and certainly the equation. Why are we doing this? What's the physics we're really after? Key ideas for you to be able to look at these graphs and recognize the slope. Let's think about that for just a minute. The slope of the velocity time graph is something that we spoke of last week. The velocity time graph slope is going to be the rate of change of velocity. And if you think back to our definition from last week when we talked about how much velocity changes, hey, that's acceleration. So the goal here is really to get you comfortable with recognizing that the slope of this graph is acceleration. Hopefully you'll also notice that same value comes up, or a multiple of it comes up from this graph. And that's the goal that we're after, to get you comfortable with this standard number 1 for our unit. And that's why we're working on this. We're after uniformly accelerated particle motion, standard number 1, that you can describe and identify and give examples of accelerated motion. So that's what we're working on. That's what this data is getting us closer to. Next up, let's go make a video analysis of a NASA movie.